All right, lesson 2 talks about power functions. So it says any function that can be written in the form of y equals k times x raised to some exponent a, where k and a are non-zero constants, is a power function. The constant a is the power, and k is the constant of proportion, or the constant of variation. We say f of x varies as the 8th power of x, or f of x is proportional to the 8th power of x. All right, then some common formulas from geometry and science. So they give us a circumference, which is c equals 2 pi r. R is our variable here, and it has a power of 1. And the constant of variation, then is just going to be our 2 pi. It's the number in front of it. Okay, area of a circle, which is a equals pi r squared. The power is the 2, because r is our variable. And the constant of variation is the constant in front of it, so it's just going to be the pi. Now, for force of gravity, we have F is equal to K divided by D squared. Now, so what we're going to do is we're going to get rid of this fraction. So we need to bring this D squared up. And remember, anytime you go above or below a fraction line, you change the sign of the exponent. So this is the same thing as saying F is equal to K times D to the negative 2. And so D is going to be our variable, so our power is negative 2. And the constant of variation in front of that is your K. And then we have Boyle's law, which is V equals K divided by P. Again, no fraction, so bring it up. So we know it's the same thing as V is equal to K times P to the negative 1. So my power is negative 1, and the constant of variation is the number that's in front of it, so the K. All right, so moving on to example 1. It says in the formula, D equals 1/2 G T squared, state the power and the constant of variation. So our power is the exponent, so it's 2, which is on T, which means the constant of variation is the numbers that are in front of it, so it must be 1/2 G. Example 2 says write the statement as a power function, use K as a constant of variation. It says the area A of an equilateral triangle varies directly as the square of the length S of its sides. So when you're trying to write this as a power function, you're going to look for where it says is proportional or varies. Okay, so we see this word here. This varies tells me equals K. Well, what equals K? Whatever's in front of it, the area of the equilateral triangle. So area equals K. Directly, and directly means to multiply, so K times what? The square of the length S of its sides, so S squared. So we end up with the equation A equals K S squared. And that's all it wanted us to do there, was come up with our equation, or the statement as a power function. Example 3, so state the power and the constant of variation for the function below, graph it, and analyze it. So we have f of x equals 2 on the 4th root of x. Now remember, we have this thing, you learned a while back, that says if you have a radical here, it's going to have a root, it's got a base, and it's going to have an exponent. And it doesn't matter if that exponent's inside or outside the radical. That you can take it and you can rewrite it as an exponential form. So you rewrite it as a base raised to the exponent divided by the root. So we can take this equation here and we can rewrite it then as 2, and it's x raised to the exponent, which is a 1, over its root, which was a 4. So this is the same thing as saying 2x to the 1/4. All right, so state the power. So what is my power? So my power is the 1/4. What is my constant of variation? Well, it's at x to the 1/4, so the constant of variation is the number in front of it, so the 2. And so we could graph this. We could come up with some points here. So like, let's see, it's a 4th root of x, so we know the x can't be negative. So let's start at like 0, and I don't know, what is a 4th root? 1 and 16, okay? So when I plug in 0, we end up with 0. When I plug in 1, 1 to the 1/4, or the 4th root of 1 is 1 times 2 is 2. And I plug in 16, the 4th root of 16 is 2 times 2 is 4. So we would have like 1, 16, and that could be our 4. So it looks like a square root. It's an even root, so it's going to have the same shape, just the numbers are a little different there. All right, so when I look at that, now you can tell me, it's because it says analyze it. And so tell me about the domain. It starts at 0 and goes to positive infinity. Because it's an even root, if nothing else, you know that even root has to be greater than or equal to 0. Raise both in 4th power, x is greater than or equal to 0, okay? Your range, you can look at it and see it starts at 0 and it goes to infinity because it's going up. Let's see, increasing, decreasing, or constant. We're increasing. Is it continuous? Yes. As far as I don't pick up my pencil when I draw it. It has an absolute minimum. Of 0. And it is bounded below because it doesn't keep going down. So those are some of the things we could analyze with that we've talked about in previous lessons. All right, so talk about monomial functions and their graphs. It says any function that can be written as f of x equals k or f of x equals k times x to the n, where k is a constant and n is a positive integer, is a monomial function. Remember, monomial is just one term. So it's not going to have any plus or minus signs, okay? For any power function, f of x equals k times x to the a, one of the following 3 things will happen when our x is negative. So when x is less than 0. So either it could be f is undefined for where x is less than 0. F could be an even function. So f is an even function, so it makes sense. Or f is an odd function. And so the graphs below represent the 4 shapes that are possible for general power functions of the form f of x equals k times x to the a for when x is greater than or equal to 0. And so we can look at these different ones. And so I'm looking at the green one here. And so we know here that it's getting smaller, therefore our exponent is going to be negative. So we could say this equation could be y equals 2x to the negative 3. Let's see, the blue line, it is increasing, but it's increasing at a decreasing rate. So we could say this is like y equals x raised to the 0.4. the red line, it is increasing, so we could just say like this is y equals x squared. Remember, we're just looking for where x is greater than or equal to 0. And then if you look over let's see, the red line on the next graph there, it is decreasing, but you could also look at it if your base is an x. There, you can look at it as if it's y equals, well, negative, because it's going down, and it could even be like x to the 1.5, okay? So it doesn't have to be numbers that we're used to seeing. It's got the shape of that negative x squared. It's similar to it, but it's just a piece of that graph. So we could say it's y equals negative x to the 1.5. All right, so moving on, let's talk about graphing power functions. So it says in example 4, to describe how to obtain the graph of f of x equals negative 2 x to the 6 from the graph of g of x equals x to the 6. State whether the function is even or odd, sketch the graph by hand, and support your answer with a graph. All right, so let's see. Describe how to obtain the graph of f of x equals negative 2 x to the 6. So let's do that part first. From x is 6. Well, what is that negative going to do to my graph? So then let's go say this is part 1. So the negative is going to make it reflect across the x-axis. And what is the 2 going to do to my graph? That's going to be vertical, because it's not inside with x. It's bigger than 1, so it's going to be a stretch. So it's a vertical stretch by a factor of 2. All right, state whether the function is even or odd. So I'll let that be the second thing. So remember, one way to check is you can plug in negative x. If you plug in negative, so we know f of x equals negative 2 x to the 6. And so if I take f of negative x, that's negative 2 times negative x to the 6. Remember, PEMDAS says do exponents first. So it's negative 2. A negative x raised to 6 powers a positive x to the 6. Compare it to they're the same. So therefore we say it's even. And then it says sketch a graph by hand and support your answer with a graph. All right, so for 3, I'm just going to make myself a table here. So pick some x's, plug in and solve for y's. And so let's do like, I don't know, negative 2 to positive 2. So I'll plug in negative 2, so I'll get negative 2 times negative 2 to the 6, which is negative 2 times 64, so negative 128. Negative 2 times negative 1 to the 6, so negative 2 times 1, which is negative 2. Negative 2 times 0 to the 6, negative 2 times 0, which is 0. Negative 2 times 1 to the 6, negative 2 times 1, which is negative 2. And the last one is negative 2 times 2 to the 6, negative 2 times 64, which is negative 128. I'll come to my graph, plot my ordered pairs. There's not a whole lot of them I can plot, but a few. All right, so I can't do negative 2, negative 128, negative 1, negative 2, 0, 0. 1, negative 2, and I can't do the 2, negative 128, but since I know that at 2 and negative 2, it's all the way down at negative 128, I know it's going down really fast. So this is decreasing very quickly here. All right, and so there's a picture of our graph. Example 5 says, to sketch a graph of g of x equals 3x to the third, state whether the function is even or odd, the end behavior, and the leading coefficient. All right, so we're going to sketch a graph of g of x equals 3x to the third. So we could just, again, we could just pick ourselves some x values. And I'm going to plug them in. You know what, I'm going to move my table, I think, over to the other side. All right, so we have 3x cubed, so 3 times negative 2 cubed. It's 3 times negative 8, so negative 24. 3 times negative 1 cubed is 3 times negative 1, which is negative 3. 3 times 0 cubed is 3 times 0, which is 0. 3 times 1 cubed, 3 times 1, which is 3. And 3 times 2 cubed, 3 times 8, which is positive 24. I'll plot the ones that I can. All right, state whether the function is even or odd. So again, we know f of x is 3x cubed. So we're going to check f of negative x. So it's 3 times negative x cubed. Remember, so it's 3 times a negative x raised to an odd exponent is negative. And so we get negative 3x cubed. Compare it to the original. It is not the same, so it is not even. It's only one term, and the sign did change. Remember, if all the signs changed, then it is odd. All right, end behavior. So, didn't say we had to write it as a limit, so I'm just going to write as x goes to the left, so to negative infinity. What's happening to our function g of x? As we go to the left, g of x is going down. It's just going to keep going down to negative infinity. As x goes to positive infinity, and so as we go to the right, g of x is going up, so it's also going up to positive infinity. And then it says, and the leading coefficient. So what is our leading coefficient here? Remember, it's the number in front of the variable with the highest exponent. So it's going to be the 3. And let me change colors here real quick just so we can see it. It is going to be that 3. Remember, that's your leading coefficient. All right. So identifying end behavior of power functions. The theorem says for large values of x, either positive or negative, the graph of a polynomial resembles a graph of the power function y equals a sub n x to the n. So whatever that leading term is what it's going to look like. Everything after it is just like what I call the bumps in the graph, okay? It's what's happening in between, but the general shape is based on that leading term. So it's just like with a cubic, okay? So when we look at a cubic, we know a cubic can look like this. We also know a cubic could look like this. These bumps in it are just based on, does it have a 2x squared or a 3x squared? Is it plus or minus? Does it have an x term? All that other stuff, okay? The end behavior, what's happening on the far left and the far right, is based on the fact that it's x cubed. All right, so example 6. It says, for the power function of the form f of x equals k times x to the n is a positive integer, fill in the table. So here, if my n is an even power and my k is positive, so think about what you know, what's an even exponent? X squared, right? And if it's a positive x squared, it's going to look similar to the one that they drew here for us. And so we know anytime it has an even exponent and it's a positive leading coefficient, it's going to have this general shape on the ends. So as x goes towards negative infinity, it's going to go up to infinity. As x goes towards positive infinity, it's also going to go up to positive infinity. Now I'm going to jump down below it there because this is if it has negative leading coefficient. So we're thinking about a negative x squared. Oops, I cut off my table though. All right, so I'm just going to, well, shoot. Let me move up just a little bit here. There we go. So I'm going to go through and write the even one again because I just want to be able to compare it. So he says it goes to the left, it goes up. As it goes to the right, it still goes up. And then here we were saying negative x squared. Okay, so I can look at this graph as I go to the left, so to negative infinity, my graph is going down to also negative infinity. As my graph goes to the right, it's going to positive infinity, but it's still going down to negative infinity. And so if you notice, when those exponents are even, those powers are even, your end behavior is going to be the same. Either they're both going to go to positive infinity, or they're both going to go to negative infinity. Now, an odd power, think about an odd power that we're familiar with. You can use x to the first, or you can use x cubed. So I'm going to go ahead and go with x cubed here. So if I have x cubed and it's a positive leading coefficient, so our k is greater than 0, then we're just looking at y equals x cubed. And that's kind of what the graph looks like there. We can see as we're going to the left to negative infinity, our graph is going to go down to negative infinity. As we go to the right towards positive infinity, our graph is going up to positive infinity. Now, if that leading coefficient, that k value is less than 0, now we're looking at a negative x cubed. So let's look at its end behavior. As we go to the left, so we're going to negative infinity, our y's are going up this time, now to positive infinity. And as x goes to the right to positive infinity, our y's are now going down towards negative infinity. So if you'll notice, if your exponent, your power is odd, your ends are going to go in opposite directions, okay? One will go up, one will go down. If your power is even, they go in the same direction. Odd power, they go opposite directions. All right, so example 7 says a match the equation to one of the curves labeled in the figure. So let's look at what we've got here. We got, look at your 1, 2, 3, and 4. And then look at your A, B, C, and D. And so let's look at, I don't know which one. Well, I'll look at number 2 there, and I notice that negative exponent. And we don't like negative exponents, do we? So let's get rid of the negative exponent on it. So I could rewrite this then. Remember, negative exponent, send it to the bottom. So this is the same thing as saying negative 2 over x to the positive 2. Well, if x is on bottom, you should know that's a rational function. And so which of these look rational to you? C. Rational functions will typically have an asymptote in it. We also know, according to this, that because x is on the bottom, we know that x squared cannot equal 0, which means x can't equal 0, which is where we actually do have that asymptote going through there. Okay, so this one here is our y equals 2x to the negative 2. Or excuse me, negative 2x to the negative 2. All right, let's see. The other one that I see might be easy to identify is D. D, notice, is going which way? It's going down. And what do we know about things that are going down? They typically have negatives involved in them. So when we look up here, I'm thinking D is going to be number 4. And so we have y equals negative x to the 4/3. Now, we just have A and B. And let's just plug in some numbers and let's check. So look at I think the easier equation to deal with is probably going to be number 1. And so when x is 1, what is the y value? Well, the fourth root of 1 is 1 times 3 is 3. So it's going to have the ordered pair 1, 3 on it. Well, it's definitely not B then, is it? It has to be A, and I could check other ones and it will work. So this is our y equals 3 on the fourth root of x, which leaves this one to have to be the y equals 1.2 cube root of x squared. So this would be B. And we can check some points on it as well to make sure that it works out. All right, analyzing the power function. State the domain and range, intercepts, and end behavior of this power function. So what is your domain? Well, notice it looks like something's going on right there at the 0, right? And if you think about this, this is 4 over x to the fourth. And so we know for domain of a fraction, our denominator cannot equal 0. And so if we solve this, we'll find x cannot equal 0. So we know our domain then is negative infinity up to 0, and then 0 to infinity. Now the range, this graph does not keep going down. Notice the end behavior, what's happening here. It's going towards a horizontal asymptote there, which is going to be at that 0. And so our range is going to be 0, not included, all the way up to positive infinity. Our x-intercepts, there are no intercepts. There are no x-intercepts because it's not going to cross that x-axis. That's our horizontal asymptote. And it's not going to cross our y-axis because that's our vertical asymptote. So there are no intercepts. And then the end behavior. So as x goes towards the left, y is going to go towards 0. And as x goes to the right, towards positive infinity, notice your y values are also going towards 0. Remember, that's the definition of how you get a horizontal asymptote. It's right there. All right, so some relative rates of growth. So it says it is important to understand that many functions tend to positive infinity as x goes towards positive infinity. It is equally important to understand that they tend towards infinity at different rates. We'll look specifically at 2 power functions and 1 exponential function now. So example 9 says let f of x equal 2 to the x, g of x equals x squared, and k of x is the square root of x. Describe what you see in the interval from 0 to 1. All right, so between 0 and 1. So I'm just going to kind of box it here so we can really focus on it. What do you notice? Which one is the smallest? Well, our red line, which is our g of x. So I'm going to put the g of x is less than, what's the next smallest? The green one, which is k of x, which is less than, which one's the biggest? F of x. Okay, what about between 1 and 2? Well, this time our green line is smaller, so that's our k of x. It's less than the red line, which is our g of x, which is less than the blue line, which is our f of x. And how can we determine what happens as x grows larger? So really there, when we're saying which one is larger, which one is smallest, what were we comparing? By the smallest, we were looking at their y values because their x values were all the same. The x values were between 0 and 1 together, or they were between 1 and 2. We're looking to see which one was smaller. We were comparing those y values. So how can we determine as x grows larger? We're just going to compare the y values. All right, complete the table. So we're just going to plug in this. So we have 2. So first off, across the top, I have different x values. I have x is 1/2, 1, 4, 9, 50, and 100. And going down the left side, I have different functions. F of x is 2 to the x, g of x is x squared, and k of x is that square root of x. And so we're just going to plug in these x values and see what we get here. So working on f of x, when I plug in x is 1/2, that's 2 to the 1/2, which is the same thing as the square root of 2. When I plug in x is 1, I get 2 to the 1st, which is just 2. When I plug in x is 4, I get 2 to the 4th, which is 16. When I plug in x is 9, I get 2 to the 9th, which is 512. When I plug in x is 50, I get 2 to the 50th, which when I put that in my calculator, it'll tell me it's 1.12 times 10 to the 15. And then when I plug in x is 100, so I'll get 2 to the 100th. That is 1.27 times 10 to the 30th. All right, then we can do the same thing with g of x equals x squared. When I plug in 1/2, I get 1/2 squared, which is 1/4. I get 1 squared, which is 1. 4 squared, which is 16. 9 squared, which is 81. 50 squared, which is 2,500. 100 squared, which is 10,000. And then I'll do the square root of x. This is a little tricky because I get square root of 1/2, which remember means it's the same as the square root of 1 over the square root of 2, which is 1 over square root of 2. And then we could keep going here, and if I rationalize it, I get the square root of 2 over 2. I'm going to switch colors here. So on the second one here, we get the square root of 1, which is 1. Then we get the square root of 4, which is 2. Square root of 9, which is 3. Square root of 50, which is approximately 7.071. And we get the square root of 100, which is 10. So it says put the functions in order from smallest growth rate to greatest growth rate. So which one of these grew the smallest amount? Well, if you look at their ending numbers there, you'll notice that k of x only grew up to 10. So k of x is going to be our smallest. And then which one is our next smallest? Well, g of x only grew to 10,000, where f of x grew to 1.27 times 10 to the 30th, which means 127 and what, like 28 zeros after that? That's a really big number. So g of x would be our next smallest, leaving f of x to be our largest. All right, and then example 11, it said in each of the choices, circle the function that grows faster. So what's going to grow faster, x cubed or x squared plus x plus 1? X cubed is going to grow faster because x cubed is greater than the x squared, the largest exponent. X cubed or x squared plus e to the x. Well, this is tricky because we don't know a lot about e to the x, but e to the x is actually going to be greater than x cubed, so therefore it's going to grow faster. And then our last one is e to the x or pi to the x. Well, remember, e to the x, e is like 2.718, and pi is 3.14. 4 approximately on both of those, okay? So which one of those would grow faster? Well, pi is bigger, so that one's going to grow faster because pi is greater than e. All right, and then some facts about relative rates of growth. The idea of relative rates of growth will be helpful in future courses. Here are some important facts to consider. Any two polynomials of equal degree will grow at the same rate. This is what we just kind of saw in this previous one. So it says x to the m grows slower than x to the n if m is less than n. So the larger exponent is going to grow faster. A to the x grows slower than b to the x if a is less than b. So if the base is smaller, it's going to grow smaller. If the base is larger, it'll grow larger as long as the exponent is the same. And then logarithms grow slower than polynomials, which grow slower than increasing exponentials. All right, so growth at the same rate. So consider functions f of x equals 4x squared and g of x equals x squared plus 5x minus 2 for sufficiently large positive values of x. We know the end behavior for the graph of g of x as x goes towards positive infinity will resemble y equals x squared from the theorem stated in example 6. Compare the ratio of the two functions for these large values of x. You can show that the two functions are growing at the same rate using algebra. All right, so here it says above, so looking at first let me look at the equations. So we're looking at f of x is 4x squared and g of x is x squared plus 5x minus 2. So notice both of them have a degree of 2. So according to number 1 up here, it tells us that any two polynomial functions of equal degree will grow at the same rate. So it's going to have to do something with their coefficients. So if we let's compare f of x to g of x. So we know f of x is going to grow, its leading term is 4x squared, and g of x's leading term is x squared. Well, when we get this, then we know that this is going to equal 4. So as x goes to positive infinity, our division is going to go towards 4. And so because we can see there, if nothing else, because our x squares cancel, because they are the same, then they're growing at the same rate. They're both growing by the 4 there. So we could say that they grow at the same rate. I think just be the easiest. And we showed that by using this. Because it becomes a constant, they're going to grow at the same rate. There's no variable left in it. Okay, our variables canceled out. All right, example 13 says use properties of exponents to compare the ratio of f of x equals 2 to the x and g of x equals e to the x and verify rule number 3 from above. All right, well, it says compare the ratios. So we're going to take f of x to g of x just like what we did in the previous one. Okay, so f of x is 2 to the x. G of x is e to the x. All right, well, there is this rule that says if you have a division problem in which the exponents are the same, you can take the exponent out and just keep the basis as division. So this is the same as 2 over e to the x. And usually you see it the other way where you like distribute the x to both of them because there's no plus or minus sign. But here we're just going to pull it out. So this is the same as 2 over e to the x. If I take 2 divided by e, it's going to give me approximately 0.7357 raised to the x. And so as my x is going to get bigger and bigger and bigger, because this number is between 0 and 1, that means this number is going to keep getting, as a whole, this is going to get smaller. So as x goes to positive infinity, our f divided by g of x is going to go towards 0. All right, if it's approaching 0, then that tells us there that rule number 3 says that 2 to the x is going to grow slower than e to the x. Because 2 is less than e. And so therefore we know that 2 to the x will grow slower than e to the x for very large values of x.